You figure if you like, you guys are experts on that right now, drawing.
I'm okay.
We'll figure out. We'll figure out today.
Oh no.
Yes, we will.
Oh no.
The last one. So refresh. We are here. We'll go through this really quick and introduce the star algorithm, which is being used for the ADC design. We did an ADC and we tipped it out a few years ago. We got a chip from TSMC. It didn't work, so it's still in the process of trying to get a functioning chip of the ADC. It's definitely not that easy, but the simulation works. I think the goal of this semester is to get a functioning ADC in simulation in Cadence. It's a lot of circuits in there. It's an 8-bit SAR ADC, has a lot of components in there. We'll probably spend maybe 2 weeks, to talk about the details of design. And you can see it has different components, including the charge pumps, the sample and hold circuits, the digital flip-flops, D flip-flops, and other things. Then we'll do our midterm exam. Then we'll start working on the cadence tutorials after that, okay? Any question on the lab? What's up?
Have you heard anything about the NDAs?
That's why I have to do it today. Just didn't even have a second to work on these things. Still have so many things on the to-do list. I mean, I will still have time, but the cadence license has to be updated. The thing is, it's two forms I have to fill up and send it back to Cadence to get a license, so our Cadence software can back to work. And then I do the NDAs, then a lot of other things. The different other like companies, Apple or other places. For smaller companies, I'm pretty sure that they have a dedicated person, like full-time employee, to just working on the Cadence server and all the license stuff. But I think for Apple, they probably have a team. Well, here, just myself. And when I was in UNLV, before Dr. Baker moved to Las Vegas from Boise State, the Cadence server has been unattended for many years. So there was a Cadence server with a super old server, but nobody actually log in and work on it. So Dr. Baker came and then he found a lab manager to start working on it. But that was a full-time employee being paid for like $80,000 a year, just working on the server and other things for the lab. Definitely, I'm not expecting anyone to do that for me, right? That's why other schools are not getting things set up, because they don't have anyone who are willing to get this done. So much work. So let's start working on that. Summarize that circuit really quick, because you guys are going to work on that. I think I extended the deadline for this one for a day. Did you guys see that in Canvas? So give you guys some time to work on it, since I was not here for office hours last week. And this one will be pretty big as well, time consuming. So be prepared for that. And the one after, same thing. It's a lot of work. I forgot which one, but I remember one of them was a 2-week lab. But since our students are getting stronger and stronger, so I just make it 1 week. But this one, no way you can get it done for 1 week. So I keep it as 2-week lab. Eventually you have to lay out this guy. It's not even considered VLSI. It's not even very large scale. It's just 8-bit mux, 8-bit OR, 8-bit AND, 8-bit inverter, 8-bit another 8-bit mux, and 8-bit high-speed FA. So laying it out is simple. Drop and place, and wiring them up is very simple. The thing is, after you press NCC, you got 1,000 errors. That's where you start, take a lot of time to figure this out. 2 weeks, not too bad. I got this one. So after that, you graduate from VLSI, electric VLSI, you never need to touch electrical VLSI anymore in your life. And then we'll move on to the cadence tutorials after that. Okay, so that will be from the end of October. So I have 1 more month to mess with electrical VLSI. Okay.
That doesn't feel like enough.
It worked last year, you know.
Well, it looks like we make most of the components in earlier labs, though.
Yeah. So it's actually reusing them, right? Putting them. Yeah. So remember that the key is you DRC and LVS the subcells before you put them together.
Yeah.
Okay. So you know if you see issues, the issues only exist at that layer instead of some lower layers or upper layers. That's a key. Right. I believe you already watched the video and did the homework. I graded already. So good job on that. And there are 2 different structures of that adder subtractor. So the first one is the one you watched in the video. These are the carries because all these flatters have how many inputs? Flatter is the 1-bit flatter, right? It's just adding 1 bit. Yeah. So all the sub modules are 1 bits. These are just 1 bit. If you want to make it into a multiple bits flatter, you just need to put them together, multiple ones. But all of them are just adding 1 bit to another bit, A0, B0. So how many inputs? There's a carry in, right? Carry in always. 3 inputs and 2 outputs. So having a carry out here, I think the first one we call it C0, right? C1 and final carry out C2. And these are the summations. S0, S1, S2. Inputs, outputs of this, how many bit flatter? 3 bits. So it's adding B2, B1, B0 to A2, A1, A0, right? That's how it works. C2, S2, S1, S0. All right. Since we know that B2, B1, B0 minus A2, A1, A0 is the same as B2, B1, B0 plus minus A2, A1, A0. And given that we're using 2's complement to represent negative numbers, so we can keep using this adder structure to change one of the addends to its a negative counterpart, like this one. So we want to change it to the negative part. We need to, according to the 2's complement operation, is flipping every single bit and add a 1 to it. So the way we do that is we add a XOR gate to it. Right, XOR gate. Doing this, and we short that input, extra input, to a control bit, which can give you either 1 or 0, and that bit is directly being fed into the overall carry in. Okay, because we know that A XOR 1 is what? So A XOR 1 is basically A1 or A1 not. So this is what? Wait, can we tell? Yes, we can. So this is gone, right?
So it's A bar.
It's A bar. So A XOR 1 is A bar. So keep in mind, you XOR something, a logic with 1, you are actually inverting it. That's a pretty important technique, a conclusion we are using in digital circuit design a lot. Okay, if you do A XOR 0, it's keep retaining that value in A. It's not changing it. So if you give a 1, right, put it to 1, you're adding a 1 to the overall input, but also you are flipping all the A's to its negative counterpart. So you are basically flipping everything and also adding a 1 to it. So it's going to perform as a subtractor instead of adder instead. If you put it into 0, It's not changing A, so A will directly be sent to the output of the XOR gates, and you are doing the adding operation instead of subtraction. So that's how we do that using XOR gate. But also, we learn the structure of the mux. I put in the assignments. A mux two transistors, inputs, the AB is 2 to 1, 2 to 1. Y. Okay, so if this is S selection bit and this is SI or inverted S selection bit. Okay, so if S is 1, if S is 1, here's 1. So this NMOS is on, this NMOS is on, and SI is 0 because S is 1, so SI must be 0, right? So this one will be on because PMOS is getting a 0 and NMOS is getting a 1. So you got, no matter what this is, it could swing from 0 volts to 5 volts because you are having both PMOS and NMOS. PMOS is good at passing ones and NMOS is good at passing zeros. So no matter what B is, it will be sent to Y, right? So otherwise, you are getting A sent to Y. So that's how that works. So that's the mux. And we can use the mux for this circuit as well. I think that's eventually it's probably what we did for the final design. I just showed you guys the massive VLSI layout, the last one, right, for 2 weeks. So I think we can also replace these ones with the mux gates. How that works. So if you use a mux, it's probably pretty simple, right, to understand what's going on because the mux is selecting one of the two, and you have A2, A1, A0 here. And inverted A, right? So you do an invert, put an inverter here as a second input. And then you have a selection bit being shorted together. So that's S. You just need one selection bit because even for this circuit, for this selection pin, you're basically just adding an inverter and send it to the other line here, right? The 2 to 1, you only need a one selection bit because you only need two different options. So only one selection bit, 0 and 1, 0 and 1, right? Same here. So selection could be 1 or 0, right? Depending on which one it is. So you are picking up either A2 or A2 bar. Okay, so definitely you want to send this S to the input to C overall carrying as well. So, but you want to make sure that when S is 1, you are picking up what? Which one? When S is 1, you are picking up which one as an input for the mux? No, A bar, right?
Yeah.
A bar. So that's how, depending on your design, right? You have to put it into a certain input to make that happen. So that's going to be, so this will be the first input in that case, because 0 will pick up the first input, and 1 will pick up the second input, which is the inverted one. So you can definitely use the mux to design a subtractor, adder subtractor as well. Which one's easier? Which one will take less space? Which one's better? Mux or XOR gate? Mux, why? Only 4 transistors. Remember, the XOR gate actually has it's just one gate, but actually it has a lot of transistors. Even for the AOI logic one, right? Even for the stick diagram one, it's still pretty big. Yeah, I think that's why we picked up the mux for the subtractor for the final final lab, 2-week lab. Any question on this before we moving forward? So now let's look at the schematic and the layout of the slider we are going to work on. You guys already worked on that, but I think there's another one this week or next week for the sliders, the high-speed slider. So it's basically another stick diagram. High-speed slider. Okay. So from the textbook, it already shows you how to derive from the original slider's logic. So it's called slider because it has a carry in, right? It's half slider, it doesn't have carry in. But slider carry in 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So all these ones. And that's a sum, that's a carry out. So look at the sum 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, right? These are all the outputs for the slider. And the next step is what before you get the logic expressions for the slider. So basically that's a workflow for for any digital circuit design, right? Just think about, so you want to implement a logic. This is all the inputs and outputs required for the digital system to implement, right? To design a digital system. That's the first step. What's the second step? So the goal is from what we need to a physical circuit, right? The deliverable will be a physical circuit. So for us, the physical circuit will be a schematic and layout, because if we know the schematic and layout, we can just put in the electric VLSI and draw the layout and send it to a foundry to fabricate it. That's a final deliverable. It's done, right? So this is the original input. From here to the final chip, what are the steps? Just think about just one simple digital block like the slider. What's the next?
Translate that into like a logic statement.
Yeah, but before that, what do we need? A K-map, right? To simplify this a little bit, right? So from the K-map, we got a logic expression. And from the logic expression, remember what we did for the last a week? If you know a logic expression, what you want to do with it? Draw the AOI logic schematic transistor level circuits, right? And then from the AOI transistor level circuits, we draw a stick diagram and implement it to the layout software so we can fabricate it as a chip. So that's from input from the input outputs to a final circuit. That's how that works. So now we have this one, and I'm skipping the K-map because this is really basic. The K-map, right? No.
It's just been a while.
It's been a while, yes. Yeah. Zero 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 one one zero. Oh no, 1110. It's just because every time I only want to flip one bit. 0 1 here. So that's for S, for example. That's for the sums. 0 0 0 getting 0. 0 0 1. You're getting 1. 0 1 0. 0 1 0. You're getting a 1. 0 1 1. 0 1 1. You're getting a 0. And 1 0 0. It's a 1. 1 0 1. 1 0 1 is a 0. Wait, what's going on? Wait, so these are all the... Oh, I skipped the row here. 110 0 111 is a 1. Mm-hmm. It doesn't seem to be very friendly for a simplification. I mean, if you just group these ones, something's wrong here. I don't think we should spend too much time on this.
Okay.
Yeah, let's don't do that. So the
It's not on the quiz.
it's on quiz, no, it's not. So for after you get the logic expression, this is a very popular FA Flatter's logic expression. We should all know that, right? I think this is right. Every single one. We couldn't really simplify anything for the sums. So it's actually A, XOR B, XOR CI. Yeah, it's gonna take another like 10 minutes. I don't think we should spend time on that. So for CI, also for C out, here, for this column, CL is A or B, CI or AB. These are logic expressions for that. Okay. So, in order to make it more friendly for the AI logic circuits for the layout design, so we moved things around and trying to put have a lot of merges and for the two logic expressions. And I think the textbook eventually, I have the derivation, it's going to take another 10 minutes. I don't think we should do that. But the conclusion from the textbook, it's giving you this. As is A or B or CI, and then C out, not or ABCI. It's just by moving things around. The textbook directly gives you this. And C out, not, becomes A not, B not, A not, B not, or CI not. So that's what we're gonna start with, right? We'll start with these guys and find out the high-speed fighter circuit. Let me see, double check. So then what is CO not though? So I feel that because this one has all the extra logic, it makes sense to convert it to this format, right? It's gonna work. But I think for carry out, this is not too bad. I don't think we should use this guy. Let's don't do this one. Let's keep using C out, which is A or B, CI or AB. That's the direct results from the K-map. Okay, so because S has all the XOR gates, I think it's getting simplified. Eventually, we're getting this for for S. Okay, I think we should do this first. For this one, AB, CI, AB. Of course, you can add 2 bars on it and start simplify things. But I think we can directly do this and add an inverter after that, because the inverter is just 2 transistors, not too bad, which is fine. Okay, let's just work on this guy and imagine that you have a bar on the top, and then eventually you are getting something inverted to this, and then you add an inverter, so you are getting this logic. Does that make sense? Okay, so let's deal with AB first. AB, 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 so right, and these two, the OR logic on the top, so they should be in series. This is A, B, and here's the CI. And this is a chicken leg to AB in series. And here's a CI. And AB. So definitely you need an inverter here. So that's C out, right? Now let's work on it. 1, 2, 3, 4, 5.
Shouldn't the where the A and B in series are connected to the bottom of the A and B in parallel, shouldn't they be connected to up left?
Here?
Up.
Here?
Yeah, so that node above the A there,
Here?
should that not be connected to like VDD? To the top of
Here? To VDD? Where to VDD?
like, because it's A or B and C in parallel with A and B. Wait.
No, it's the NOR logic here. That's the NOR here, right? So these two blocks should be in series on the top, according to the NOR gates.
Okay.
Yeah, let's slow it down a little bit. So consider this as a box, right? And this is the box.
Okay.
Okay? So these two boxes should be this for P, right?
Right.
And within this is a smaller box for A and B. A and B should be this, right?
I see it. Yeah.
Yeah, and this is A, B, C, I.
Okay. Yeah. I see.
6. 1, 2, 3, 4, 5. 6 nodes and 5 transistors. Two in parallel, pretty simple. A and B. And then you got a two in parallel, but you got two in series first. So this should be pretty simple as well, since you can just do this and this, right? And then for the P, for the N moles, so since we have A and B here, so it's better to have A and B here, directly go to ground for this branch. And then it encounters CI first and then A and B in parallel. So C first and two in parallel. Right? And now let's try to align it, see if that works. Because this has to follow A, B, this order, and this doesn't matter, so we want to label it A on the right and B on the left. And then you have A, B, C, I. So I have two here, so these two has to be A, B. It's following an order, and it starts from this node, so it's A, B, and CI, right? So for here, so if I do it this way, it won't be aligned because this has to be CI. but I can definitely, because this one doesn't really matter, I can definitely change it, right? I can change it. I just change this right here.
Yeah.
So in that case, this is CI aligned, and AB like this, and AB like this. Okay, so carry out is done. We need an inverter. We just add an inverter. It won't take too much space at all. It's easy, even though it's not a one-liner. It's fine, right? Just keep it the same height. It's the inverter. Wait, no. Sorry. So that's the input. It's taking the output from here. And that's the final output. That's C out.
Yeah.
Done. So that simple circuit can figure out carry out. So for S, you can see there's no bar on the top. For this case, there's a lot of logic inputs. We don't want to complicate it. So let's directly use this logic, and then add an inverter at the back, on the back. So let's see. Let's do the schematic first. So that's a NOR gate, right? So do this, and these are in parallel. Three in parallel, and three in series and in parallel with CL, not. So, because we have this one, you see, I think this is probably why he designed the circuit this way. Since we are getting CL here, right? But this node is directly CL not, can be directly used for this signal input, just saving a lot of space. So that's why you want a CL not to be here as one of the signal input. It's already available, right? Okay, cool. Now let's draw the bottom part. First, these three is the chicken leg, so we directly draw three in series in the row, in the column. And for the other part, so that's a NOR gate structure. It has to be a pretty big lag. So these three are in parallel, and this one on the top, right? According to the experience, if there's a single one, we prefer to put it on the top. So do CL not first, and then three in parallel. One, two, three, 7. So 7 transistors. We need 8 nodes. That's a lot. 2, 3, 4, 5, 6, 7. So 3 in parallel, we know how to do it. Okay? And then immediately 2 in parallel, basically. Okay, 2 in parallel, 2 branches. So based on experience last time, we want to think about this a little bit. So instead of redrawing everything, so 2 in parallel, we can do this, and now it's where we want to decide which one should be the 3 in parallel, which one should be the single one, like this, right? So I think we want to do here. So these are the 3 in series. This is the one single one here. And then for the unknowns, so 3 in the row first. So for these ones, we know it's ABCI, right? For one of them. And I can see for the ABCI, they're from A, B, and CI in that way. So it has to be usually ABCI to one direction. So we're going to name it as ABCI. If we do it here, and we got a ABCI aligned, and then the next one, we hope it's this guy, because the next one here is this guy. So this one has to be CO naught. Okay, it goes through here, and then reaches this point, which is here, this point. And you have 3 in parallel. So this becomes pretty simple. You just do this. So 3 in parallel after that, single one. Okay, so in that case, because here it's in a certain sequence, it's A, B, C, I. So we're going to define these as A, B, C, I as well. And this is CO naught. It's perfectly aligned. Okay, so for the lab, you don't have to follow the whatever the logic expression from the textbook, right? So I think it uses a different one. I don't think that's necessary. I think the classic CL logic expression here works perfectly. We are not seeing any problems. You got this, and you got this as well. So according to the stick diagram, you draw the layout, okay, for the lab. Right. Any questions on anything by far? So for the quiz, it will be a last stick diagram problem, and it's from the logic expression to AOI circuits with transistors, and then stick diagram. So a little bit different from the last one was you have to simplify the logic expression first, otherwise it just looks like too long. It won't be able to figure anything out, it's just too much. So keep in mind, simplify it first. Try to recall any of the knowledge you learned from logic, and simplify it down to a smaller circuit, and then design the schematic and layout. Okay. Right, now let's work on it.